Hello everyone, my name is Sang Hong. I'm from University of Connecticut. It's my honor to give a presentation on my recent research. Today, I'm going to talk about flexible and stretchable smart insert pressure sensors within multi-wire carbon nanotube and PDMS double-layer composites. This is outline. First is I will present the recent wearable device and limitation of pressure sensors for human motion and gait analysis. And then I will explain our sensor fabrication process and their results. And finally, I'm going to summarize these presentations. Recently, wearable devices have obtained a considerable attention in various research fields. Also these days, with increasing interest in health monitoring such as physiological signal and physical signals, many studies on wearable smart devices have been widely studied. To realize such a wearable device and achieve accurate and high output signals from humans, wearable sensors have to have comfortable and conformal contact with the human body. So in order to use the wearable sensor during daily activity and exercise, the sensor have to be thin, flexible, and stretchable. With increased interest in health monitoring such as human motion and gait disease, many research groups interested in instrumented insole sensors. For example, one of the commercial insole sensors is pre-integrated with various instruments such as pressure unit sensor, accelerometer, and wireless communications. However, even though this completely integrated system provides practical variety and reliable information, it's difficult to use these systems for individual user applications because of their high cost. Also, it needed to have specialized shoes. So in order to address that issue, some academic research groups have been developing different approaches using commercial sensor and their self-developed systems. However, the use of commercial sensors, they limit the scalability of wearable applications. There is another issue regarding existing insole sensors, which is deformabilities. So in order to address that issue, highly stretchable, comfortable, and scalable sensors are required for practical wearable applications. Recently, for demonstrating such a sensor, flexible and stretchable materials consistent of elastomer and conductive materials have been focused as your sensing materials. However, sensors with the materials, they have some problems such as hysteresis, low linearity, and small pressure sensing range. So in order to improve sensitivity, the limitation, and sensing ranges, some research group focused on morphology or microstructures of sensing materials. When you look at this slide, by introducing various microstructures, they can effectively improve the sensor performance. However, although these microstructure sensors are appropriate to achieve high specific performance, there still are challenges for wearable insole system. So for the wearable insole system having a wide pressure response range, advanced approach are definitely required. This slide shows device fabrication process. As you can see this schematic to fabricate MWCNT PDMS films, firstly, MWCNT solutions was prepared by dissolving carboxyl functionalizing MWCNT powders in IPA solvents. And then ultrasonications was carried out to disperse the MWCNT in the solvents. After that, PDMS was mixed with the MWCNT solutions using ultrasonications for 30 minutes. Afterwards, in order to remove the IPS solvent, heating process was carried out at 100 degrees for 2 hours and then curing agents added into MWCNT PDMS mixtures. This slide shows the fabrication process of pressure sensor. After preparing the composite mixtures, the mixture was poured into a mold with a height of around 150 micrometers. After curing in vacuum ovens, the composite films was filled off from the mold and then cut into pieces with appropriate size. So finally, the composite films show flexibility and stretchability. Also, for stacked double-layer composite films, this process was repeatedly carried out. And then, to demonstrate a single or double-layer pressure sensor, the composite films was pressed on a PI substrate with copper interdedicated electrodes. And for connections, copper wire and silver paste used. Then pressure sensors were encapsulated by using PI tapes. So as you can see, the figures is the shear flexibility. To investigate the structural composite materials, we performed Raman spectral analysis. From Raman data, we found that news-free peak related to CNT was appears after adding multiple CNT into PDMS, which means that the multiple CNT were disposed into the PDMS materials. Also, we found that when increasing multiple CNT concentrations, GP indicating the multiple CNT increase. Also, the degree of multiple CNT dispersion and surface morphology of the composite materials were investigated by using SEM. So as a result, when you look at the SEM image, we confirm that multiple CNTs were dispersed in the PDMS matrix, and the composite film has a random distribution surface structure, which might be caused by the IPA solvent evaporating during curing process. So it's supposed that a random distribution surface would improve the sensor performance more than a smooth surface due to the increase of effective contact areas. This slide shows shear resistance and thickness of composite films with different multiple CNT concentrations. From the data, we found that the shear resistance decreased with the increase of multiple CNT concentrations. In this study, we define a B6, T7, or B7, T6 materials as a stacked double layer. Here, B6 means bottom composite layers with 68% multiple CNT. And T7 means a top composite layer with 78% multiple CNT in the stacked double layer. B6 T7 or B7 T6 film show around 220 and 58 ohm scale respectively, and the shear resistance are dependent on a bottom layer. Also, as you can see SEM image of cross sections, single layer have about 160 micrometer of thickness and double layer have around 330 micrometers, regardless of multiple CNT concentrations. This slide shows the related change in resistance of composite sensors under different pressures. As you can see the data, all the sensors exhibit two distinct regions with different sensitivity. In case of single layer sensors, when the multiple CNT concentration increased from 6 to 78%, the linear response and the pressure range limitation were improved up to around 280 kilopascal and 2 megapascals respectively. The enhanced results attribute to the decrease of distance between neighboring multiple CNTs due to high field composition ratio in the PDMS matrix. In case of the stacked double layer sensor, which is B6 T7, this sensor shows a similar trend to single layer sensor with 7-8%. This result indicates that there is no any improved performance. On the other hand, B7 T6AA sensor exhibit an excellent linear range up to around 700 kilopascals and wide pressure ranges of 2 megapascal, which show great potential in extreme fields of wearable device. The results indicate that top high and bottom low concentration alignments make the pressure sensor show gradual change in resistance under pressure change, which means that an order of alignments for the stacked double layer sensor is important factor to achieve higher linearity and a wide pressure range. This is a mechanism of stacked double layer composite sensors. In general, sensor performance strongly rely on a proper concentration on conductive fillers in elastomer-based composites. According to that, we focused on MWCNT concentration as your fillers to investigate the mechanism of our sensors. As you can see this slide, in case of the B6T7 double layer sensors, the top and bottom layer would be simultaneous presses, regardless of low and high pressures. That's why the sensors show a similar tendency to single layer pressure sensors. On the other hand, in case of the B7 T6 double layer sensor, the top layer would be initially pressed, but bottom layer would not be affected on the low pressures. And on the high pressures, both the top and bottom layers would be pressed at the same time, which led to that the gradual change in resistance occurs like the schematic figures. So as your results, if you consider gap or resistance gradients of the stacked double layer composite films, we could obtain higher linear sensitivity and a broader pressure range. This is the application of MWCNT PDMS pressure sensor. To demonstrate a practical Insoo sensors for wearable application, the stacked double layer pressure sensor, which is the B70 T6 structures, were attached on shoes insole and then connected to Arduino for recording output signals. As your results, as you can see the data, the Insole sensor exhibit excellent ability to detect the motion states for walking, running, and jumping because of high linearities and wide pressure ranges. Also, we did the operational stability test by applying 4500 cycle and 400 kilopascal pressure to the sensors. As a result, the sensor operates stably without significant degradations. Accordingly, from the results, it's supposed that the stacked double layer pressure sensor could be applied in the field of wearable healthcare for human gait-related disease. Let me summarize my presentations. We demonstrate double-layer MWCNT PDMS-based pressure sensors with their gap gradients by stacking two different concentration composites. As a result, the pressure sensors show higher linear range and a wide pressure range, which can provide extensively potential application in monitoring human motions. Also, to demonstrate practical Insole sensors for wearable application, we fabricate some Insole sensors using the double layer composites. And the Insole sensor not only can classify user motion states, but also exhibit good stability for long-term use. Finally, we believe that the double layer gradient structures provide an effective approach for potential application in extreme environments that require high linear response and a broad pressure range. Thank you for watching the presentations.